So now, after we did solve an example for one-dimension diffusion transient problem, we will promote the level of complexity now to two-dimension transient problem. Still, the central finite difference method is applicable to multi-dimension transient problem. So in this situation, you are dealing with a two-dimension problem. So let's set up the grid here. Again, this is node I plus 1, I minus 1, j plus 1, and j minus 1. And now, again, for simplicity, this is going to be delta x, and this is going to be delta y. And to simplify the math, delta x would be assumed equal to delta y. Now I can draw the control element surrounding the base node, which is I. Dimension of that control element is delta x, delta y, right? Now, if I would like to drive an equation for that node I for two-dimension transient problem, I will start with my model, and my model is simply Laplace equation, but in this case, the right-hand side is not going to be 0. So I'm going to have partial 2t by partial x squared plus partial 2t by partial y squared equal rho Cp over k, which is 1 over alpha partial t by partial time t. Now we can discretize the equation using the central finite difference method. So partial 2t by partial x squared will be ti plus 1 minus 2ti plus ti minus 1 divided by delta x squared plus tj plus 1 minus 2tj plus tj minus 1 divided by delta y squared equal to 1 over alpha, and this will be ti minus ti divided by delta t. But now we are solving explicit transient for simplicity here, so everything here would be marked by the previous, right? Now multiply the equation by delta x squared. Delta x squared, delta y squared will cancel out, so I will end up having ti plus 1 plus ti minus 1 plus tj plus 1 plus tj minus 1 minus 4 ti. Everything here is marked by the previous time step. Then in the right-hand side, I will have delta x squared, alpha delta t over delta x squared, which is simply 1 over Fourier's number times ti to that new time step minus ti to the old time step. Now I'm going to multiply by Fourier's number. Then I'm going to bring that ti to the right-hand side. You will end up having, in a simple language here, Fourier's number times ti plus 1 plus ti minus 1 plus tj plus 1 plus tj minus 1. Then you will have minus 4 Fourier's number plus 1 times ti at the time step p. This should give me ti plus 1 at the new time step. So this is the governing equation for interior node. So any interior node, you can apply this equation. And again, you have a stability criteria. To select your time step by having this coefficient is greater than or equal 0. So you have Fourier's number less than or equal 1/4. That's a stability criteria for interior node. That's the case here for applying the finite difference method into two-dimension transient. You also can apply the energy balance method. So this is the central finite difference method. Also, I can apply the energy balance method, and I should get the same equation for an interior node. So if I draw my grid again, same one. This is I plus 1, I minus 1, j plus 1, and j minus 1. Control element is here. Then energy balance equation is total energy in, or dot, plus the total energy generated should equal to the energy out plus the energy stored. Okay, again, for the energy balance method, nothing is going out. So far, we are not considering any heat source. So the total energy in should equal the energy stored. And what is the energy in? That's Q1. And this is Q2, Q3, and Q4. So you add up all the four Qs, it's going to give you En. So Q1 is simply K, right? Times the area, which is going to be delta Y times 1. 1 is a depth, multiplied by Ti minus 1 minus Ti divided by delta X, plus Q2 is going to be K, still delta Y times 1, Ti plus 1 minus Ti divided by delta X, plus Q3 from the top, going to be K. The perpendicular area is delta X times 1, Tj plus 1 minus Ti divided by delta Y, plus Q4, going to be K delta Y times 1, Tj minus 1 minus Ti over delta Y. That should equal to the energy stored. This is MC partial T by partial time T. Mass is rho times the volume times C or Cp, partial T by partial time T. And the volume is the volume of that control element. So I will have rho delta X delta Y times 1, Cp, then Ti P plus 1 minus Ti P. Since we are solving explicit here, then I'm going to divide that by delta T. Okay. Then everything here would be P, 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 P. Again, delta X equal delta Y, cancel out, cancel out, cancel out, and cancel out. Then this will be delta X squared or delta Y squared. Divide by K, you end up having Ti minus 1, Ti plus 1, Tj plus 1, Tj minus 1. These are the first four terms here. Then you have minus 1, minus 2, minus 3, minus 4 of Ti, very similar to this. And in the right-hand side, you will divide by K. So I will have Ti plus 1 plus Ti minus 1 plus Tj plus 1 plus Tj minus 1 minus 4 Ti equal to, I will have rho delta X squared Cp divided by K delta T. K Cp rho, K Cp rho will make a combination of 1 over Fourier's number, then Fourier's time delta T, this will be actually 1 over alpha, then alpha delta T delta X or divided by delta X squared, that give you Fourier's number. So this will end to be 1 over Fourier's number times Ti P plus 1 minus Ti P, and I'm going to mark all these temperatures at the previous time step. It's very similar to this equation. If you simplify, you're going to end up by the same equation we got for interior node. So either you use the energy balance method or you are using the central finite difference method, you can end up having the same equation for interior node. So what about the if you have non-interior nodes? Again, you go back and visit any of your heat transfer books. You will find there is a series of tables very similar to what we had for the two-dimension conduction problem. So this is the table I just described here. This is showing the explicit and implicit method for central finite difference transient, and it's showing a specific case like an interior node, and this is the equation that we got recently, and the stability criteria related to it. Then if you have other cases like a corner point, convection exposed point, or another corner point exposed to convection from a different side. If the case is not present in that table, the only way to do that is to drive that using the energy balance method. Also keep in mind this table is driven for assuming delta X and delta Y are equal values. So that's in a simple language how to use or upgrade the finite difference method transient analysis in two-dimension problem. My next step is actually start looking for solving a two-dimension problem using the center of finite difference. I will solve that problem under steady-state condition. Then we would like to do the transient analysis for it and see if we can run the transient for a longer period of time. We should reach the steady-state condition. Just to show you how to apply the transient finite difference method for different cases like interior node, node exposed to convection, and these are exist in the table, but also I will include additional cases that is not in the table to show you how to use the energy balance method to get that nodal temperature. Then we solve steady and transient and compare the results.